Hi, in this video we are going to talk about searching algorithms. So for searching, the aim is to find the index of a given item, of course. There are two main approaches, the linear search and the binary search. A linear search, as the name suggests, in an unsorted array we have to iterate through the whole array sequentially, checking every item. And it has a linear time complexity because we have to go through from the beginning to the end until we bump into the item we are looking for. And of course we are going to return the index of the given item. On the other hand, binary search we can do better if the array is sorted. So we find the position of the target value within a sorted array in logarithmic time complexity. What's the difference between linear and binary search? Linear search can be used for both sorted and unsorted arrays. But if the array is sorted, we can do better. Instead of linear time complexity, we can do logarithmic time complexity far better with the help of binary search. But it's very important that we can only use binary search if the array is sorted. The binary search algorithm begins by comparing the target value to the value of the middle element of the sorted array. So we not start at the beginning, we start at the middle node. And if this element is greater than the item we are looking for, we continue the search on the left subarray because we know that every item after the middle element is greater, so it cannot be the item we are looking for. So we can discard half of the array. And that's why the complexity will be linear, by the way. So if the element is less, then we search the right subarray. And we can implement binary search in a recursive manner. So why is it good using binary search? As I have mentioned earlier, we can discard half of the items on every iteration, and that's why it will have logarithmic time complexity. And is it a good approach? Yeah, it is a good approach. For example, binary search trees relies heavily on binary search. We will have nodes, we will have children's, both left and right children, and we can come to the conclusion that with the help of this tree-like structure, we can use binary search. And why is it good? Because instead of linear time complexity, we can do logarithmic time complexity very, very fast. Okay, so how, for example, what about linear search? Linear search is quite straightforward. We just iterate through the whole array and check whether the given array index, I mean the item with the given index of the array is equal to the item we are looking for. And if it's true, if they are equal, then we return the ith index. Anyway, I'm going to return 0, which means that we are not able to find the given item in the array because there is no such item. So this is, I think, pretty straightforward how to use it. For example, we have, okay, now a sorted array. I'm going to use linear search, but we should use binary search instead. For example, we try to find 22 and 1, because arrays in Java starts from 0, then this is the 0, 1, 2, 3, 4, 5. And we have printed out 5, so it's working fine, linear search. What about binary search? Binary search, we are going to use two methods, and we are going to override these methods. First of all, we specify that what are the item we are looking for, and then we are going to call this private method, which is recursive. So of course the starting index is 0. The end index is the array.length minus 1, y minus 1, because we start at 0, so we have to decrement the value by 1. And of course we are looking for the item. And as we have discussed earlier, it is a good approach if the array is sorted, we start at the middle index. So start index plus end index divided by 2, it is going to give us the middle index. Of course, if the end index is less than the start index, then we return minus 1. Or we could do, it means that the start index should be less than the end index. Then I'm going to call this binary search with the end index, start index, and the item. Okay. And anyways, if the item is equal to the one we are looking for, So these are the array item, and this is what we are looking for. If they are equal, it means that we have found the item we are looking for, so we just return the middle index. Anyway, the item is less than the item at the given middle index in the array. It means that we have to traverse the left subtree, and that's why we go from the starting index to the middle index -1, because we have already examined the middle index, so we do not have to specify the middle index. We can specify middle index at -1. And else it means that the item is greater than this array middle index. It means that we have to traverse the right subtree in a recursive manner. So the middle index +1, this will be the starting node, and the end index and item. So if I use, for example, the binary search, okay, it's going to return 5 again. So how it works? This is the starting index, this is the end index. We start approximately at the middle, for example this. Then, for example, I'm looking for 5. The middle index will be this, and we come to the conclusion that the item we are looking for is 5, is less than 22. We are standing. So we come to the conclusion that we just have to examine this part of the array. We don't have to bother about this because we know that it is greater. It is greater than 22, and we are looking for some value that's less than 22. So this will be the start index and this will be the end index. We bump at the middle node. If it's, by the way, odd, then of course we end up with something like this. 6, and we have to compare. 6 is greater than 5. Yeah, it is greater than 5, which means that we can discard this part of the array, and we just have to consider this part of the array. So that's why it's very, very powerful binary search, because we can discard half of the given array on each iteration, and that's why the complexity will be logarithmic. So that's all about searching. Thanks for watching.